of the day by Miguel Montero, Harvard. And Miguel has 4 lectures in 4 days. So we learn about, I guess, recent development in swampland conjectures.
Miguel,
right. Please.
Okay, thanks very much. Let me first open the lectures. Aha, there we go. Voila. So you guys see my oops. Sorry about that. First time doing this. Okay, good. Okay, so you guys see my slides, I think. Everything is good?
Perfect.
Okay, well then, thanks very much, Mari and all the other organizers for putting together this this very nice school. And thanks to all of you for coming to listen. So I think Irene, she already gave the first lecture. It was an introductory series of lectures on the Swampland. And I'm gonna take the other end of the stick. I'm gonna be telling you about how to use the stuff that she's been that she describes to you. How we've been using it very recently under the course of the past couple 3 years to get exciting results in the Swampland program. Okay, so I'm gonna delve a little bit more into the technicalities of the stuff that she okay, that she told you about. Okay, so the plan of the lectures. Okay, as Maddie said, we have 4 lectures here. So I will start with I will start with by discussing consequences of the conjecture that Irene already explained today, absence of global symmetries. Okay, so that's a very nice thing, but what can we do with it? Well, you can actually do a lot. So I'm going to start with that, and in particular, I'm going to focus on a very cool consequence of no generalized global symmetries, which is the completeness hypothesis here. So the completeness hypothesis allows you to get to use Swampland principles to predict. It's the simplest Swampland principles that allows you to predict new particles, which is very, very interesting. And that will be the what I will basically cover today, if I have time. If not, we'll run into the second day. There's no problem. The thing that I cover right afterwards is is another consequence of no generalized global symmetries, which was put forth 3 years ago, which involves symmetries involving changes in space-time topology. It's called the covariation conjecture. It's a proposal of Kumrum Bafa and his PhD student Jake McNamara, and has had far-reaching consequences also in the Swampland program. I will spend one lecture describing this one because it's very interesting. Is the core of a lot of the cutting-edge research that we're doing at the Swampland program, and has interesting implications. And then I will use these two on the third day to describe a set of results that have been that we've been working on over the past few years, which is the idea that once you combine this no global symmetry story with and you apply it in situations where you have a lot of supersymmetry in very high dimensions, Swampland principles become so strong that they are actually one is actually able to use them to fully classify all consistent string theories in quantum gravity, achieving what we call string universality. So this is a very recent result. We've basically been able to show, based on Swampland principles, that in 9, 10, 9, and 7 dimensions with supersymmetry, string theory is, so to say, the only game in town. The only effective theories consistent with Swampland principles are precisely the ones that you get from string theory compactification. Okay, so this will be maybe part of day 2, but certainly most of day 3. And finally, for the last day, I will switch gears, and in day 4, I will describe an application of a different Swampland principle, the Wigger-Arty conjecture, which, if I'm not mistaken, Irene will introduce in her lectures tomorrow. And I will apply the Wigger-Arty conjecture to de Sitter space. And applying the Wigger-Arty conjecture to de Sitter space, you get a new kind of bound on the particle spectrum, which is called the Festina-Lente bound. And this bound, again, I've chosen to present in these lectures several things which have strong consequences. Okay, so the Swampland program is very exploratory. We are learning many new things. And I find everything that we learn interesting, but not everything has very strong concrete consequences on this or that. And I try to focus on things that do. So the pristina lente bound is a bit more speculative than the Swampland principles, but has very strong consequences, okay? Good. So let's get right on with it. But before we do that, there's a very important warning that I need to make. Okay, it's very, very important. Perhaps the most important thing I need to say in this lecture, which is that you should please ask questions. Okay, you should ask questions all the time. This is particularly important given that this is an online set of lectures. So I'm not seeing your faces. I'm not seeing if the lecture is being boring, interesting, if the message is getting across, or if I'm losing you guys. So please, please, please interact me at any point with any question you like. And if at some point you have questions, you know, sometimes one has questions, but doesn't really feels a bit shy, or you need to think a bit more about it before asking the question, which you shouldn't, by the way. Like, for instance, when I was a student in Europe, the feeling in Europe is that you only ask questions if the questions are very smart. When I moved to the US, everybody asks every kind of question, no matter what it is, no matter, you know, they don't think 2 seconds about it. I think this is in this one thing, I think this is the better way to do it. So just ask any questions. But if it's difficult for you, you can also email me, okay? This is my email. All right. So let's get on with it, okay? Very good. Yes. Okay. So let's begin. Okay. So no global symmetries. Okay, so Irene explained there's no global symmetries in quantum gravity. Okay, and so the first thing I'm going to be telling you about in this set of lectures is about a new set of symmetries, which is called generalized global symmetries. Okay, this is a generalization of the notion of symmetry that has become a mini revolution in quantum field theory and string theory over the course of the past 5-6 years. So starting with a paper in 2014. Let me find the reference for you. So that's 1412.5148, and it's by Gaiotto, Kapustin, Cyber, and Willett. By the way, another important thing, if my handwriting is difficult to understand, let me know, okay? Okay. So this kind of thing, there's no global symmetry in quantum gravity, and there's this new kind of story called generalized global symmetries. So of course, the whole point is that there's also non-generalized global symmetries in quantum gravity. And you might ask, well, if there's no global symmetries, why are we starting the lectures discussing generalized global symmetries? And the reason is, and I think it's an important principle, so I'm going to write it down, so that we can learn a lot, not just from existence of symmetries, which is what we do in quantum field theory, but also from their absence. And this second way of thinking about symmetries is more the way that we work with symmetries in the Swampland program. Okay. So we use symmetries to try and we first start with an effective field theory that looks like it has some symmetry. We understand how it's broken, and by understanding how it's broken, we learn something about the theory itself. Okay. Any questions so far? Okie dokie, very good. So let me start with a simple example, which I think Irene discussed in her lectures, of what do I mean that we learn things about symmetries. I think Irene mentioned this one. So for instance, the standard model has a symmetry, which is called B minus L, it's baryon number minus lepton number. And if you just look at the standard model Lagrangian, it's a broken symmetry. It's a global symmetry, okay? So this is like a global symmetry in the standard model. But in quantum gravity, we know it is either broken or gauged. So if it's broken, that means that we should observe processes that tell you how the symmetry is broken. Like for instance, neutrinoless double beta decay. That's a process that breaks B minus L. The other possibility is that it's gauged. And that means that there's a fifth force coupled to B minus L. So we should be able to say see a fifth force, which is experimentally constrained to be very weak. So its gauge coupling is less than 10 to the minus 26 by experiment. Okay. So this is already telling you something interesting, perhaps about the standard model. But the whole point of this set of lectures is to extend the kind of symmetries that we can talk about and from which you can learn interesting stuff. So enter generalized global symmetries. Okay. So,
sorry, that one assumes symmetry is not broken, right? If it is broken, we don't have this bond, right?
That's right. That's right. There's two cases. So there's two cases. So what we know is that there's no global symmetry in the standard model. So it can be either broken or gauged, and these are two different cases. You're correct. In the second case, you have a fifth force, and the fact that we have not observed it puts this upper bound on. If it exists, if it's case number 2, that's the upper bound that we get on the gauge coupling. In the first case, that's a different case where it's broken. You can measure, you can see processes violate B minus L symmetry in the standard, which we haven't observed. So one example would be beta decay without emission of neutrinos, because you could emit 20 neutrinos. And the other one would be, for instance, just Majorana masses for the neutrinos would lead to this effect. Sorry, would be implied by absence of global symmetry or B minus global symmetry. So it's telling you.
Then they would have a lower bound on the gauge boson mass, right?
So for this one, if we go for the case of gauge, we don't have a bound on we wouldn't have a bound on the gauge boson mass. It could be massless, as far as we know. It might be possible to get a bound on it coming from Swampland principles. Okay, so combining with other principles like Wigwright conjecture, you can actually try to put a lower bound on the mass. So you can say, well, the gauge coupling is very small, so if it exists at all, it has to have a lower bound on the mass. Or actually, with the techniques I'm thinking of, which are coming from a certain paper by Matt Rees, where you would be able to put an upper bound on the mass. So you can say it's either 0 or mass. Okay. Any other questions? Okay.
May I ask a question?
Oh yeah, please.
Sorry, is this no global symmetry works for discrete symmetries like parity or charge conjugation as well?
That's a great question. That's a great question indeed. We believe that this is also true for for discrete symmetries. So discrete symmetries have to be broken or gauged. Now, the case you were talking about was parity. Okay, so parity. Okay, and indeed, it's true in string theory compactifications. It's either, depending on which theory you're looking at, it's either an exact symmetry of the theory and it's gauged, or it's broken. So for instance, parity, it's an exact symmetry of type 2A string theory. And in type 2B string theory, so it's a gauge symmetry. And type 2B, it's not a symmetry, so it's broken. Already at the level of the 10D supergravity Lagrangian is broken. So yes, those apply.
Thank you.
Okay, so then let me start with extending a bit the notion of symmetry to what we call generalized global symmetries. Okay, so what is a symmetry really? So when you study it in the undergrad, it tells you it's a charge that commutes with the Hamiltonian. And that is true in quantum mechanics. In quantum field theory, we actually associate to a symmetry, we associate a current and charge operators. So what happens is if you have some situation where I'm drawing time, and here's a word line of some particles, okay, they do whatever, they carry some conserved charge. There is a conserved current, okay, and a charge operator, which we can define at any time-like surface. So we pick time-like surface like this, and we pick the normal vector, which is just time-like. And then the conserved charge is okay. Well, now you guys are all seeing my passcode. Okay. Okay. So there's this operator, which is conserved, which is the charge operator, and it's very simple what it does. When we say this is zero, actually it is not exactly zero. It's so if you imagine,
Sorry,
is there a question?
sorry, we don't see your tablet screen.
Oh, you don't see the tablet? Oh, damn. What happened? Sorry about that. So, okay.
Good. It's coming.
Okay. Okay, good. Sorry about that. All right. So when you have something like you have a conserved charge like this. If you just have the particles, so these are the particle word volumes, particles. As you know, what do we do in quantum field theory? Well, in quantum field theory, we actually create particles by inserting local operators. Yes, so we can put a local operator here if you want, O of X, and another one here, O of Y. And if you look at this, there's an operator equation, which is there's a current which is conserved. The fact that it's conserved means that this charge operator, which you are constructing by integrating this operator over some surface S, doesn't really matter if I integrate it on a different surface S prime. So if I have a different surface S prime here, doesn't really matter, because what this operator is doing is counting how many particles are intersecting its word line. So here's 4 particles, and here's 4 particles as well. The only place where this can change is if, for instance, I have, let's say this goes like this, and I insert the operator here, where, you know, I move away. There's 2 local operators in which the word lines of 2 particles end. So if I shift to the surface S double prime, it can change because there's 2 local operators that create particles. So the proper way of quantifying this is to say that this is not 0. As an operator equation, this is only equal to the locations of operators. So for instance, in this case, OX plus OY or whatever, you know, the divergence of the currents is just the insertions of local charge operators, okay? And that's what asymmetry is. This equation, which I'm gonna rewrite here more clearly, I hope. It's what is called the word identity of the symmetry. And it's the reason why we like symmetries. This kind of thing allows you to simplify computations. You are not computing a correlator, you know, and you have an insertion of currents, then you can use this kind of equation to simplify the correlator, and that's why we like symmetries in quantum physics. Okay. Any questions about this picture of what is a global symmetry? It's just it's the description that you have in textbooks. Only I emphasize a bit more the pictorial aspect of it. The fact that it's really just about operators that count the number of word lines of particles. Yes? Any questions? Okay. Very good. So, oh yeah, this is our question. Sorry, I couldn't quite hear. Okay. So, well, once I present this picture like this, it's very clear that the symmetry, the way I introduced it, this symmetry is associated to local operators. And why is that? Well, because local operators create particles. And this is why this appears on the right-hand side of the word identity. Okay? From this point of view, one could ask, why not try to extend to operators that create strings, for instance, or branes? Some other extended objects that we know they exist in string theory and actually in quantum theory. And so the idea that you extend this notion of symmetry to extended operators is what we call a generalized global symmetry. So for instance, the picture I drew before, I had particles. Here I have particles. But what if I instead have like a line instead of a local operator that creates a particle? So I'm drawing time again here. What if I have an extended operator which creates a worldsheet of a string? For instance, this is a one-dimensional operator, creates the worldsheet of a string. Okay, and it's the same thing. The worldsheet of the string cannot break, so it's actually you can associate a conserved charge to this word volume. Okay, so how will we go about describing this more quantitatively in terms of equations and not just with drawings? Well, for ordinary symmetry, we have an operator. We have charge operators. So I have the charge operator, which is of dimension 0. And then we have a current of dimension 1. Okay. So the way to generalize this is to generalize global symmetries. Is that you have charge operators of dimension p for any integer p. So for instance, this is the case where I drew here p equals 1. And then there's also a current. And you see, for the 0-dimensional case, the operator had dimension 0 and the current had dimension 1. So if the charge operator has dimension p, the current has dimension p plus 1. Okay? And the fact that it's a symmetry is the same thing as saying that one has a word identity. So this thing, which is, I don't know, you guys are familiar with this notation from notations in terms of differential forms. So this is like a p plus. So p plus 1 is a fully antisymmetric tensor with p plus 1 indices, nu, so on and so forth. This is equal to 0. Okay. So in the same way, you can define a charge operator, which is just the integral of the Hodge dual of G equals 1. Okay. Under a surface which has dimension d minus p minus 1. This dimension is chosen such that you have something that can link with the word volumes of charge operators. So this is a surface which has codimension p. So it has, so you know, in the same, when you have a surface, you have a number of in d dimensions. It has codimension p, has p, a basis of p orthonormal vectors. And so this thing is just this guy, etc. Then you take the product with all the normal vectors. Okay. So just like so just to connect with the previous case, for instance, if we for a moment set p equals 0 here, and we are in 4 dimensions, then d minus p minus 1 is equal to 3. And that's the case we're describing here before. We integrate the current. To produce the charge, we integrate the current on a surface which is like a constant time surface, which is a 3-dimensional surface. Okay, so dimension 3. Okay. And the fact that this thing is a symmetry means that if you insert the symmetry operator somewhere here to capture the fact that there's a string, it doesn't really matter if you insert it here or here. This is what this equation is saying. Okay. How to see that? Well, if you have the operator Q on some surface S, and you have some operator Q prime on some other surface S prime. So here are two surfaces, S and S prime. Then you can fill in the volume, and you can say that Q minus Q prime is equal to the integral on this volume V of the derivative of JP plus 1 by Stokes' theorem. So this is Stokes. And this thing is 0 because of the word identity. And so it doesn't really matter where you insert the symmetry operator. So that's the connection between these two perspectives. Okay. So all of this has been a bit of an abstract discussion. I told you what a global symmetry is, and it's a bit abstract. So I'm gonna try to make it more concrete by focusing on a concrete example, okay, of what the of a concrete theory we all know and love with a generalized global symmetry. But before I do that, are there any questions about this? Is it clear? Is it not clear? Please, there's a question.
Excuse me, I may have missed something, but why do we call them global symmetries if they have charge and current? I guess I missed it.
Right. So global symmetries also have a current. Maybe the thing you're thinking about is about gauge charges for which the current is coupled to a gauge field. Okay. So for instance, let me give you the simplest example of this. Which I think was also discussed in the next lecture, and I'll write it here. So consider the theory, okay, a theory which has a Lagrangian, with just a single scalar phi, and you have this Lagrangian, okay? It's just the theory of a scalar. Now, the equation of motion of this theory okay, is this. And so you can rewrite it as this for J1 equals D phi. Yes?
Yes.
Okay, so this is a theory which has a global symmetry. It has a current that allows you to compute the charge, but it's global, it's not gauged. So if you want to gauge it, what you do, okay, is you actually change the Lagrangian to something like this, and you couple to the gauge field, okay? And now
yes.
the current is coupled to a gauge field and can be measured from far away using the gauge field. But global symmetries also have currents. Did I answer your question?
Yes, sure. Yes.
Okay. Any other questions? Please ask away. I mean, the whole point of this is to send a message. So if this is not getting clear, please ask away. I think for global. Oh, Martin also has a question, please. Martin's iPad has a question. You can unmute yourself and just ask. Also, you don't need to raise hand. You can just interrupt me, okay? Let's do it American style. Just interrupt me. This is not something I would do in Spain. Like in Spain, you wait until the professor finishes, but in America, it's like, wait a minute, let's do it like that. I think it creates for a more lively atmosphere. Martin?
We can unmute yourself, Martin.
Okay. So well, but if you want, you can send me an email with your question later, perhaps, or if you forgot. Or okay. So very good. So let me give you an example to make all of this much more concrete, and I'm going to do it with a theory we all know and love. Very simple theory, which is an example. Okay, so let me just draw a separation line like this. Example of a generalized global symmetry, and I'm going to make it in Maxwell theory. Okay, so this is just electromagnetism. I mean, electromagnetism without electric charges. Okay, so I am gonna forget about the fact that the real world has electrons, and I'm just gonna describe the theory of pure electromagnetic fields. How do we do that? Well, we know there's a Lagrangian, which I'm writing like this in covariant notation. This is the gauge coupling. So F mu nu, which is equal to this in differential form notation, F hot star F. By the way, I am using differential form notation. How familiar is everybody with differential form notation? Meaning, okay, are you familiar with, I am assuming you're familiar with expressions like this? Yes? Who is familiar with expressions like this? Please raise your hand if you're familiar with an expression like this. Okay, I've seen everybody. Oh, okay, a lot. Oh, 6, 7 out of 23, 6, 5, 4. Okay. Let's see. Okay, so some, but not all, are familiar with notation of differential forms. Okay, so I'm gonna try to write things both in differential form notation and in this other notation, but differential forms are very useful in theoretical physics in general. Okay, so anyway, you have this theory, and it has some equation of motion. So this is the equation of this is the equation of motion of Maxwell theory. It's just the hot star of F equals 0. That's the differential form version of it. You might be more familiar with its more standard notation. These things are the same. Okay, and these equations are famously invariant under a gauge symmetry, where A goes to A plus D lambda, where lambda is a function. This is the differential form version of it. The non-differential form is that A mu goes to A mu plus D mu lambda. If you shift the gauge field like so, nothing changes, it's not observable, and in fact, we identify two configurations if they're related by this thing, which is called a gauge transformation. Okay, very good. So this is Maxwell theory. It's very easy. It's a free theory. The equations of motion are linear, but we can still do interesting things with it. I told you that generalized global symmetries is about having extended operators in a theory. So let me construct an extended operator in Maxwell theory. Suppose I take the gauge field, A, here it is, and I integrate it on some cycle C. Okay? This is something I can do. Now, if the curve C where I'm integrating has endpoints, okay, has some endpoint P, then this integral is not gauge invariant, because integral over C of A plus D lambda is going to be equal to integral of A of C plus integral of C of D lambda, and then we're going to be able to see that this is, oh, sorry about that, it's integral of A of C plus lambda at P1 minus lambda at P0, where I'm putting the endpoints P1 and P0. So this is not gauge invariant because it changes under gauge transformation. But what if I just take a curve Z, which is a closed loop? Then there's no problem. And actually, people introduce these operators, which they call Wilson lines, depend on a curve C, and they are described as the exponential of I Q integral of A over the closed curve C. Okay? In quantum field theory, one is used to operators that are associated to points. For instance, you compute F mu nu at a point X. This operator is not associated to a point, to a single point X, rather is defined over a curve, a closed curve. So this guy is called the Wilson loop. So Wilson loops are very, very useful in quantum field theory. Okay, they appear, they can be used to study confinement and the like. They're very useful objects, and they come with a parameter Q, which is it is an integer, and we call the charge of the Wilson loop. The reason why we call this a charge is because morally, what the Wilson loop is doing for you, it's allowing you to introduce probe sources into the theory. Okay, so imagine that you're in a laboratory, and you're describing an experiment in which there's no free moving charges, there's no electrons, so you don't need to worry about free moving electrons. So you can use free Maxwell theory, but still you need to put your magnet in there, or you need to put some source in there, and the source you have is some very heavy particle with charge Q. The Wilson line is the mathematical way that you introduce such a probe in the theory. So physical interpretation, there are probes in the theory. Okay, so once you have one of these guys, actually, it's easy to see what happens if you are computing something with an insertion of a Wilson line, because the insertion of the Wilson line, okay, shows up in the right-hand side of Maxwell's equations. So there's something like at every point where the Wilson line is. So there's the delta of the where the of x minus x Wilson line. Okay, this is space-time. So okay, so you parameterize the Wilson line by some parameter s, and you integrate over ds. And so this is what this is telling you, is that when there is a Wilson line, the equation of motion gets modified as if there was a massive particle inserted in the location of the Wilson line. Okay, so this thing is precisely the equation of motion that we have here is, if we write J2 equals F, we can write this equation as d of J2 is equal not 0, but it's equal to something which is basically 0, except where we introduce some charged line operator, the Wilson line. And this is very similar to the equation that I had for the zero form current, which was the divergence is 0, except where you introduce local operators. So this theory, Maxwell theory, free Maxwell theory, has a one form, what we call a one form generalized global symmetry. And the current of the symmetry is just the field strength. Okay? And the charge operators are these Wilson lines. Okay? So this is the basic example I wanted to discuss of a generalized global symmetry. It's the simplest example. It's discussed at length in this paper by Gayotto, Kapustin, Cyber, Willy that I described. And now I'm going to tell you what we can do from Swampland point of view with this generalized symmetry. But before I do that, are there any questions about the Maxwell example? about this example of a generalized global symmetry? No questions? Okay, if you have a question later. Oh yeah, it's their question. Okay. Oh no, there's no question. Yes, is there a question? Please ask.
Sorry, can you hear me? Excuse me. Can you hear me?
Yeah, I can hear you.
Okay. Why do you call this global symmetry? I didn't get the point. This Wilson loop is somehow non-local, but if it's a contractible cycle, this C, then somehow it seems that you can contract it to some point, and somehow it can be local.
Absolutely. Okay, very good. This is great point. Thanks for asking this. Okay, good. Yes. So Rock is saying, okay, fine. So you want to say this is some non-local version of the global symmetry, but then I draw a closed loop. So can't I just always, shrink this loop to a point? If I can get rid of things, how is it conserved, right? So the point is that I could be doing this, okay? I could be doing all of this in geometries. There's 2 points to it. First of all, I could be doing it in geometries. I could be doing it perhaps in space-time with non-trivial topology, where there's a non-contractible curve, and then I can wrap the line around the curve, and then there's no way you can contract it and make it disappear. But more importantly, perhaps, all of this is a local statement. So even if you have a collection of, you have a collection of Wilson lines like this. Okay, so there's one like this, and then maybe there's one that links like that, and there's another one that links like that. Okay, then you cannot move this to the vacuum before you hit one other line. Okay, so when there's more than one, they can actually lead to non-trivial charges, so to non-trivial configurations, how they're linked. Okay, and that's how you can measure this kind of things. But that's a great point. If you just have a single Wilson loop by itself, not doing anything, that's morally the same as saying that I have in the local symmetry case, an operator of charge Q, and next to it, the operator of opposite charge. That's just stupid. That has no charge. So here, to make non-trivial configurations, you need to put the loops in ways that that they link non-trivially between each other, or you need to use space-time with non-trivial topology. Did I answer your question?
Okay, thank you.
Mm-hmm.
Yes, thank you.
Okay, any more questions? This was a great question, by the way.
Sorry, there was a problem with my voice. Can I ask?
Please.
I want to ask, is this symmetries, for example, when we say this symmetry is global, is it dependent on the observer or not? All of the observers see this symmetry global.
Yes, absolutely yes. So if you give me more context, I can try to address the question in a more specific context that you're thinking. But yes, absolutely, all observers agree on what the global symmetries of the theory are. And furthermore, if you give me a given quantum state or a given configuration of operators in the Euclidean picture, everybody agrees whether it has zero charge or non-zero charge and how to compute it. Yes, global symmetries are observer independent. Gauge symmetries sometimes are other matters. So sometimes where you have a duality, a gauge symmetry that is apparent for some observer using some duality frame may not be apparent in a different duality frame. But for global symmetries, this is not the case. I don't know if you have a more specific question in mind or if I address your question.
No, I got. I wanna, for example, we have two observers, A and B. Okay. One says that this symmetry is global, and observer B says that no. I suppose that this symmetry is gauged. Is it possible?
That's great. That's great question. No, that's not possible because these two observers would agree on the following. It's very simple. and this is completely general lesson. I think it was in Iran's lecture, but this completely general lesson because when one learns about gauge theory, it can be very confusing because a lot of people say very different things. But the basic thing that distinguishes something being gauged, okay, is whether you can measure it from far away without getting into the system, okay? So for instance, let me give you an example. Suppose I could do this with local symmetries, okay? But let me do it with one from symmetries because this is the new symmetry I'm describing, but it's the same argument, okay? Suppose I have a configuration of, you know, like line operators, which are linked in some interesting way such that the charge is non-trivial. And suppose here we have observers A and B. They're looking at this kind of thing, okay? Now, suppose I go and I say, okay, observers A and B, I'm actually gonna be evil and I'm gonna cover all of the interesting configuration with a shroud. I'm gonna cover it. So you cannot look at it directly. Can you still tell me where are the charges here? Well, if the charge is global, there's no way. No, they need to remove the shroud. They need to go in with their measurement apparatuses and measure exactly what this thing is. If this charge was gauged, okay, then they can actually do the following. They can, even if I cover it with the shroud, they can take a surface very far away, okay? So away from the shroud, away from the configuration, and measure the total integral of the charge far away using some sort of Gauss's law. So the point is that in gauge theory, when you have charges, the source gauge fields, and the gauge fields can actually be measured from far away, and there is no way to screen them. So if you can measure from far away, it's gauged. If you cannot measure from far away, it's global. And that distinction is the same for A and B. Did I answer your question?
Yes, thank you very much.
Okay. If at some point it's not super clear, we cannot stay. So maybe we cannot stay discussing forever, but you can send me an email and we can discuss over email or at some other point. Okay. So this is a one from global symmetry. Charge operators are Wilson lines. So great, I just perfect, just in time. I'm very happy. So what can we do with this from quantum gravity point of view? Well, the point is that we are told there's no global symmetries in quantum gravity. And so there's no generalized global symmetries in quantum gravity either. So suppose that this Maxwell theory we're discussing is not coupled to gravity, then it cannot be. This is the equation. So this is, I'm gonna write it in terms, it's the same equation, okay, for a two-form current. Okay, this cannot happen in quantum gravity. It just cannot. So if someone comes and tells you, how do we fix this? What do you do about it? Well, about the only thing that you can do, the only thing that you can do is to say, well, I mean, let me copy the equation again here to illustrate what I'm gonna do. So this is the equation that cannot happen in quantum gravity. How can you change it? Well, you can just say there's no Maxwell field. There's just no F from the get-go. So you change the question completely. Okay, fine, you can do that. But I know there are examples of quantum gravity which have Maxwell, and maybe I'm interested in having a theory with Maxwell because after all, our world at low energies is described with electromagnetism. So what do you need to do? Well, suppose that I add something to the theory, some other operator, such that this thing changes as an operator equation. Okay, so suppose that to the Lagrangian that I had before, the Maxwell Lagrangian, for instance, I add another term, which maybe is a Dirac Lagrangian, where this A is the A here. So it's the same gauge field, okay? Then when you work out the equations of motions of this theory, they are d hot star F equals to something basically what is called the Fermion current for this thing. Okay, so this is no longer zero. The divergence is no longer zero. We have broken the symmetry, and now it's okay with quantum gravity. So breaking, the basic lesson I want to teach here is that breaking a one-form symmetry, which we need to do in quantum gravity, is achieved by introduction of charged particles. Okay. So this, let me stop a moment here to emphasize how remarkable this is. You start with a theory which has no charged particles, and simply by thinking about black holes and quantum gravity and all of that, you conclude that the theory must have charged particles. If you talk to a quantum field theory person, they tell you Maxwell theory without particles is the perfect quantum field theory. It's perfectly fine. It's a free theory. We can define it non-perturbatively. It's the easiest kind of theory, honestly. But in gravity, this is not true. You need to introduce charged particles. So quantum gravity, you could say, is, in a sense, if you think of this Maxwell theory as the Maxwell theory in our world, quantum gravity is predicting the electron. It's predicting there has to be a particle such as the electron. Okay? And in fact, it's not only predicting the electron. Let me give you a bit of a perspective, of a more intuitive perspective of why adding particles breaks the one-form symmetry. Well, you see it already at the level of the equation here. The divergence, the current is no longer conserved. The divergence is zero, so it's not a conserved current. But you can also see it at the level of lines. Once you introduce electrons, okay, you have a charge operator, gauge charge operator psi of x, which is not gauge invariant. If you do a gauge transformation, it transforms like this. So it's not a good operator. We are supposed to only look at things which are gauge invariant. So this operator is not good, but there is a very nice way to fix it. Suppose we write an operator which is integral. Suppose that this field has charge q, okay? So then this transforms like this. So suppose we put a Wilson line on some open line L now, L, and at the end point, we write psi of x. Okay? Before, when I tried to write down an open Wilson line, it was not gauge invariant. But now, if you do a gauge transformation, the variation coming from this term cancels the variation coming from this term. And this whole operator is gauge invariant. So introducing charged particles. So charged particles allow Wilson lines to break. They can break. And now, I think Sarok was making this point like, what if I can contract the line to a point and there's no charge? And I was telling him, well, you know, if you link them like that, then you cannot do that. But now that I added charged particles, you can, because you can do something like this. You can just open lines. You can put a charge operator here, and you can just open. And once you open them, it's obviously, if you can cut the lines open, there's no way that you're gonna get anything conserved, okay? So adding charged particles in this way, this is a more pictorial way of seeing that the symmetry is broken. But it's also important for this, what the nice thing that this picture realizes is that we must have a psi of x, psi q of x, we must, for every q. Remember, the Wilson lines that are introduced here, they come with this charge parameter, this q. And this q is like it can have integer values 1, 2, 3. If there's a single operator that cannot be broken, then there is a global symmetry in the theory. It can be discrete. But if there's a single one which cannot be open, there's a global symmetry. So to get rid of the global symmetry, you need to be able to break all the lines, which means you must have charged particles of every charge. Okay? Okay. This is very general, and this, I think, illustrates really the power of Swampland approach. Just by thinking about global symmetries, you learn to the idea that in every quantum theory of gravity, all possible charges have to exist as physical states on the spectrum. Okay, this idea, which we've got from this global symmetries idea, it's called the completeness principle. Okay, and this completeness principle has very, very interesting consequences. For instance, it has consequences for the particle content in our world. It has consequences for string compactifications. It has many, many consequences. In a sense, it allows you to predict string theory, which is something that we'll discuss tomorrow in the next lecture. So since we're near the time, and this is a very nice stopping point, I think, let me perhaps wrap up here. Just to summarize, we have discussed how to extend the notion of symmetry to generalize global symmetries, which involve extended operators. Okay. And then we have discussed what it means to break those symmetries. To break those symmetries means to introduce charge operators so that the extended operators can break. So you introduce charged particles in the spectrum, and this leads to the idea that every possible charge in any quantum theory of gravity is actually represented by physical states on the spectrum, which is the completeness principle. So I'll wrap up here and take any questions you might have about these or any other thing that I discussed. Thanks very much.
Thank you, Miguel. Great talk.
Thank
So
you.
we have for questions. Everybody, please. Yes, there is one question.
Please, Navid, please. Navid, you can just unmute or yourself and just ask away. If there's a problem with the mic and you cannot and we cannot hear, you can also type your question in the chat.
Yeah, maybe.
Yeah, maybe we'll go with. Yeah, let's go to Sharok, and then we go to Navid afterwards. Yeah.
Excuse me. I have a question about this Q.
Yes.
Is that you're saying that any Q, any real Q is allowed, if I understand correctly?
No, sorry. That was my bad because I was too quick. Because this is not the main point of the discussion. Not every Q is allowed. Okay. Only integer Q is allowed in a certain normalization. Okay. And this has to do with the fact that okay. So this has to do with the fact that this is a different story than the one I talked about, but basically these lines are not the only lines I discussed. So I told you that the Wilson lines, are about putting some probe particle in the theory, and the fact that the charge is quantized means that the probe particles that you're introducing have quantized charges. Now, why do particles need to have quantized charges? Well, in the real world, particles have quantized charges because of Dirac quantization. Because if there is a monopole on the spectrum, there has to be a relative quantization condition between the magnetic charge and the electric charge to avoid inconsistency. You can make a similar argument at the level of operators, okay? So on top of Wilson lines, there's other lines which I haven't discussed. So there's actually two one-form symmetries in Maxwell theory. It's an electric one-form symmetry, which we discussed, and a magnetic one-form symmetry, where the charge operators are called tough lines, okay? And these tough lines describe what will happen if you would introduce a probe magnetic monopole in the theory, okay? And so there's actually the proper quantization condition is that this thing is in the integers. Okay, so you can if you normalize things such that the monopole charge is 1, then you know that the charges for the Wilson lines is also integers. Okay, at the level of operators, what you want is that the operators are, what we call mutually local. That if you have a correlation function of several operators, the correlation function really only depends on the positions of the operators and not on other data. And this only happens if the charges are quantized like this. Did this address your question, or?
Okay, yes, because I was thinking if it should be real, then it's not consistent with the, for example, anomaly cancellation or something like this. So, I mean, from the point of view of the quantum gravity, you're saying that any charge, any integer charge is possible. But from the other side, in the quantum field theory, for example, in QED, we have few charges. I mean, in the standard model, we have few particles. So how is it possible to have all of these charges?
Very good, very good. So, very good. Okay, so there's an important caveat here, which is I only need that there is a state with that charge. Okay, so I am allowed to consider multi-particle states. Okay, so for instance, I can have a Wilson line. Suppose I give you in the standard model. Okay, I give you Wilson line with charge 1,000,000. How do I end this Wilson line in the standard model? There's no particle with charge 1,000,000. Well, sure, but I can put an operator here, which is the electron field, which has charge, let's say 1 to the power 1,000,000. Then that's a local operator with charge 1,000,000. Okay, so it's about having all possible charge states. Okay, now you might ask, okay, fine, Miguel, if you allow for multi-particle states, so there's just really a few particles, what is this giving you new? And for instance, for the standard model, this is something I will describe in the next lecture, but just to get ahead of things, for instance, you know how in the standard model, there's this weird thing that the quarks have electric charge 1/3, they have fractional electric charge. Well, so Swampland, depending on something called the global form of the gauge group, it's telling you there has to be, so the quarks have charge 1/3, and they're in the fundamental representation of SU3. Using completeness, you can also conclude, for instance, there has to be a particle which has charge 1,3, but it's a singlet of SU3. This particle has not been observed. Okay, and it's simply because states with this kind of charges you cannot construct with the charge in the standard model. So it is predictive, and I'll describe exactly how it becomes predictive for the standard model in particular tomorrow.
Thank you.
I think, okay, so there's a question by Navid in the chat, I think. Does existence of horizons somehow affect the definition you said about global and gauge symmetries? I mean, the ability of measuring charge from far away. Good question, very good question. No, it doesn't. Otherwise it would be a bad definition, because this shroud I described could be a black hole, right? So how does that work? Well, suppose you have a particle with electric charge Q, then you can measure its charge from very far away if the charge is gauged. Suppose you throw the particle into a black hole. So actually now I can just draw the black hole. This is nice. I don't need to do anything. I just gonna draw the black hole. Here's a black hole. Okay. Black holes have electric charge still. Okay. The electric field lines that are coming out of this particle can actually escape the black hole. So there's a solution of black hole which has electric charge Q, is called the Reisner-Nordstrom metric. So the metric is like this. Okay, and so you can measure the charge from far away. It also has electric field, and you can measure far away. Electric field can escape a black hole. That's the basic idea. I hope I was clear. If not, just shoot me an email. Maybe we can go to Imanpur, because I don't think there's a lot of time anymore.
Sorry, when you add charges to this theory, you still can have closed loop Wilson loops. Okay, so it seems you haven't gotten rid of the global symmetry completely.
Good. So the thing about these Wilson loops, okay, is I think is what Sharok was. This is hinted at in Sharok's question. It's not so much that you can draw them, it's that you can draw them in a way that you cannot destroy the link. Okay, so if you have a couple Wilson loops or something like that, okay. For instance, if I keep this loop fixed, there's no way I can shrink these guys to a point. Okay, Sharok was saying, well, if you have a single loop, clearly there's no charge because you can shrink the loop to a point and it disappears, which is true. If I add charges, okay, I can still unlink this because I can do whatever configuration of loops you give me, I can always do this. Oh, I didn't want to do that. Let me redraw the loop again. I can remove like this. I open it up a bit and I add a charge particle like this. Once I do that, I can start moving it, okay, without touching anything else. So everything is topological. Oh, sorry, this you know, I'm just removing it. So once you can open them, any configuration becomes topologically trivial because you can always unlink them like that. And then I can do the same here. I can go here, put the particle to the other endpoint, and then I start doing like that. Okay, and then the same for the last one, and then I end up with nothing. So adding charged particles, which allows me to break open the loops, is enough to break the symmetry. Was that clear?
Yeah, but what about the scalar theory when you have phi and a mu? So for phi constant, what happens there?
So what theory you're asking about? Are you asking about
when you couple scalars to gauge field?
Couple scalars or something like that? This theory?
Yeah. You still have a global symmetry changing phi by a constant, okay?
Oh, well, okay, good. So not really. So here's the thing. Remember, in quantum gravity, you can make symmetries global or gauged. So in this model, gauge invariance means that the symmetry where you shift phi plus c, okay, it's actually, okay, well, it's part of a larger set of symmetries where phi goes to phi plus c of x, and then a goes to a plus dc. Okay, so what happens is this transformation, which this is the one you're talking about, right?
Yeah.
Good.
Yes.
This transformation in this theory is actually, I think Irene might have mentioned this, is what is called the global part of gauge group. So we have a gauge transformation here, okay? And it's more general than this. It allows for spatial dependence. It's clearly gauged. And then this transformation is a special case, of the other one, okay? When that happens, okay, when you have a gauge transformation that doesn't go to 0 to infinity, which is what is happening here, it's what is called the global part of gauge group, and that's a whole other story. But these transformations are precisely the ones that you use in measuring gauge charges from far away. So you're right. You're completely right. In this case, this is an exact symmetry, but it's a gauge symmetry because it can be reached from a continuous deformation of gauge symmetries. This one is not global symmetry, or rather it's what we call the global part of gauge group. It's an actual symmetry, acts on physical states, but it's okay in quantum gravity because you can, it can be measured holographically from far away. Was that convincing?
Yeah, but I don't see why you are not allowed just transform phi by a constant and not transform a. So that seems to me a global symmetry. But
let me explain why you're not allowed to do that. Okay, so you're actually allowed to do this symmetry and then you transform a, but you're not off the hook. You cannot say, so for it to be a global symmetry, an honest global symmetry that is not the global part of the gauge group, it will have to be that transformations like this are not symmetries of the theory. Okay, the moment that these transformations are allowed, then this one becomes the global part of the gauge group because it's just taking this constant. And the point is that in this Lagrangian, well, you must have gauge symmetry for the gauge field. So A must transform like this. And once A transforms like this, it's unavoidable that phi transforms like this to cancel the thing.
Okay. Thanks.
Any other questions?
Any other question?
Okay. Good. So I'll be back
Yeah.
tomorrow explaining some of the consequences of completeness. I'll introduce completeness, experience, and consequences, and we will keep pulling the thread, and we will end up talking about how talking about no-global symmetries leads you to discuss topology change in quantum gravity, and a version of no-global symmetries, which is the strongest, more modern version, is called the covariation conjecture. So I'll discuss that tomorrow. Thanks very much for attention and for all the questions.
Thank you very much. Thank you, Miguel. So we reconvene in 18 minutes.